Quantum mechanics and information theory are great 20th century inventions. The graphic here shows a transition from a spatial distribution of waves to one of particles. This is created by duality. This is the point of quantum mechanics, to describe how continuous physics becomes discrete. But this graphic makes no sense. Fields are not described by distributions of particles. Wave-particle duality is often cited as a counterintuitive aspect of quantum theory, but the discontinuous transformation between physical distributions and discrete measurements is both elegant and natural. The transition from continuous to discrete is not an approximation of the physical world. It is an inherent aspect of the physical world. Quantum mechanics is the science of making continuous physics discrete. Information theory is the science of relating discrete measurements with data. Quantum mechanics is essential to understanding modern optics. Information theory is essential to imaging. Computational optical imaging is where these two disciplines come together. Accurate descriptions of the relationship between objects and measurements are essential to this process. We call these descriptions the forward model. Chapter 2 introduces the basic concepts of forward models. The most important concept is discrete data values, such as particle measurements, accurately describe continuous object states, such as waves. So let's get started in understanding what this means. Computational imaging. Episode 2, Modes. All right, so we're digging into Chapter 2 of Computational Optical Imaging. Chapter 2 covers forward models. So we're going to talk about modes, which is how we turn continuous functions into discrete values. Then we'll talk about transformations of functions and how we can implement various transformations on discrete forms of the functions, how we represent the functions using either wavelets or neural representations or Fourier representations. We'll talk a little bit about noise, resolution, and image capacity, and that will conclude our discussion of forward models. We'll move on to Chapter 3 to talk about inverse problems. Okay, so we're going to talk about modes, and this is the classic version of a mode situation. We have a particle in a box. Here the particle is confined within the game of Pong. So we see that now we're getting into this wave-particle duality issue. We think of that there's this continuous particle, but if we measure the particle, we would measure the particle at some position. And we can think of a distribution would be what's the probability that we would measure the particle at some position within the box. So the distribution we might describe as a function psi of x, and then across this box there'd be some value of psi of x, and in this particular case maybe it would be uniform. But usually in a physical situation we have a distribution over some space, and then there's boundary conditions at the edge of the space. For example, we may require that the probability go to 0 at the edges of the box. So these distribution modes shown in figure 2.2 are various distributions for that boundary condition, that the probability distribution is continuous and goes to 0 at the edges. Those are what we would call the modes, something that satisfies the boundary condition and also describes a distribution within the box. Okay, we'll back up a little bit beyond the mode. The modes consists of family of functions. A function is a relationship between input values x and output values f of x. So f of x here would be on the y-axis, and f of x has one value at each value of x. So this is what I've just sketched here as a function because it has exactly one value at each point x. If I sketch something like this, this is not a function because it has more than one value at each value of x. But if we think of like a physical distribution like temperature or wave radiance, that's something that's going to be have a single value at every point in space, and it will consist of a function. Functions can have various properties, of course. One property that's interesting would be a periodic function. So if we have x and then the function exists over some interval but then repeats again this exact same function over another interval, well, that's what we would call a periodic function. A function is periodic if f of x is equal to f of x plus L for some period L. So the sketches I just made are kind of, obviously pretty rough versions of a periodic function. The classical versions that we think of with periodic functions would be, for example, the sine functions, the harmonic functions. Here we've plotted sine of x with various periods. So the period again is period 1, going here for, let's say, 0. The function is 0 at x equals 0, and also is 0 at x equals minus 1 and x equals plus 1. We're going to, throughout these discussions, use Python to model various systems and imaging and functions. Here's some simple Python code that's showing that we use the NumPy function sine of x to plot x with various periods. So the Python code for these lectures is on the Arizona Camera Lab GitHub site, and you can go and review each image that we make. The functions that we use, so we have a very simple version of a function. Now we'll go to something a little bit more abstract. We consider images as being built from features or distributions. These are functions, and the functions exist on a vector space. So a vector space is a set of objects such that the objects are the set of objects is closed under addition and scalar multiplication. So if I have an object psi of x, one of my functions, I multiply by a scalar alpha, that remains a member of the set. And then if I had two members of the set, psi of x and phi of x, and I add them together, they're also members of the vector space. So we'll consider various vector spaces in thinking about distributions and images. For example, we may be interested in the vector space of functions defined on an interval of length L. Okay, so the members of the space are these functions f of x, and f of x has the property that it has some value for between minus L over 2 and plus L over 2, and it's 0 outside of that interval. So this is a function with compact support. Now, if I have a function that satisfies these properties, and if I add that function to another function satisfying the properties, it will still be 0 outside the interval and will still have some value within the interval. So this space is closed under addition and scalar multiplication. Another very, very similar function is the set of functions with period L. These functions can be thought of as identical to the functions with compact support on distance L, because we could just say that we're going to evaluate these functions such that outside of the interval they evaluate to 0. So these two vector spaces, the set of functions periodic in L and the set of functions that are with compact support on the interval from minus L over 2 to plus L over 2 are the same vector space. Now, when we have a set of functions, we often choose to represent the functions on some basis. So, for example, the periodic functions can be represented on the harmonic basis. So this is a Fourier series. If I have a function that's periodic in L, then I can represent the function as a sum over all the harmonic functions, in this case expressed in exponential form. Now, this function f of x expressed in this way is obviously periodic, because each one of the harmonic functions is itself periodic. So if I take any sum of periodic functions, it will remain periodic. It's less evident that this is an accurate representation of f of x, and so we'll look into that in the next couple of slides. The component of each Fourier component of f of x is found by projecting f of x onto that Fourier component using the integral relationship here, that we integrate the inner product of f of x with each Fourier component, and that gives us the discrete value f sub n that we use to describe or project f of x onto this basis. Okay, so as I said, we're going to look at these things using Python and Jupyter notebooks. So here's the Jupyter Notebook looking at the Fourier representation of a signal with compact support. In any Python notebook, we begin by importing some library functions, especially NumPy and Matplotlib, to allow us to analyze and just display functions. And then in these Python notebooks, we can add text cells that will describe what's going on with our functions or with our analysis. In this case, we define a function that we're going to use to think of for analysis. Now here, this is a function defined on the integral minus 0.5 to plus 0.5. So we have a function with finite support. This function is defined simply by saying, it's 0 for to the left and 0 to the right, and in between it has a linear sloped region between 0.25 and minus 0.25 and 0, and then from 0 to 0.25 it has a value of 1. So we've defined this function, and now even though we define the function with finite support, we can equivalently think of this as a function that's periodic over the period of support, but that we're going to replicate, that we're going to analyze using Fourier analysis. So there's a lot of ways for us to go about completing the Fourier analysis, but a lot of times if we're just exploring systems with Python, we don't have to get fancy or clever about how we might do this math. We can just ask the program to do the math for us. So in this case, we're actually going to define the function, and then we integrate using this integrate.quad integration package. The inner product of the function with the sign for pop here is the order of the function. So pop is an integer going from plus or minus 0 or 0 to infinity. Now, instead of using the complex valued harmonic function, we've used the sine and the cosine, and then we can add the sine and the cosine coefficients together to create the Fourier expansion in complex form. And so then once we have the projections, this SV and CV are the projections of the function onto the sine and cosine functions, we can go here in Python and create the function as a Fourier series, where we're just going to add the evaluation of the Fourier series coefficients together to get our estimate for the function. We can do that for variable numbers of Fourier coefficients. So in this, on the upper left, we've used the first 5 Fourier terms, and by adding those terms together and evaluating them, we see an approximation to the original function. Then we go to 10 Fourier terms, 20 terms, and 40 terms, and we see that the estimate gets better as we use progressively more Fourier coefficients in our expansion of this function. So the proof that this is a basis for the function, that we can describe any periodic function on the Fourier basis, would consist of showing that as the number of terms goes to infinity, the error between the estimated function and the true function would go to 0. Now, this is the function evaluated over its area of support. Because we've constructed it as a Fourier series, of course, if we evaluated it beyond the period of support, we would see the function repeat periodically, which is what's shown here. Okay, going back to our expansion onto the Fourier coefficients, again, if we showed that as we add more and more Fourier terms, the error goes to 0, then we have this idea that we can represent the function as this discrete Fourier series. So we've taken a continuous distribution f of x, and although we can evaluate it at any value of x by using the Fourier series, we're really describing the function. In the first case, if we have 5 Fourier terms, then we have these 5 coefficients that we would use to describe this single function at infinitely many points in space. Or we could describe the function with 10 or 40 coefficients as we go forward, but still a very small number of Fourier terms is describing the continuous function. And here we're evaluating it at several hundred points to make the plot using just those 40 discrete values. So that's the power of this method, is that we now have the ability to represent continuous functions with a very finite number of mathematical terms. Now, many functions we could describe as having some limited bandwidth, meaning that the Fourier coefficients go to 0 for the order greater than some value. And here L is the spatial extent of the function. B would be what we call the bandwidth of the function. And so B times L is a number. And so we would say that the function is band limited if the Fourier coefficient terms go to 0 for n greater than B times L. And this is also a vector space. This is the space of band limited functions. If we add two band limited functions together, that remains a band limited function. If we multiply a band limited function by a scalar, that remains a band limited function. This number of coefficients that we need to describe the function, now actually we would have n going to negative values as well as positive values. So the number of the coefficients we need to describe the function would be 2 times B times L. And so we call that the Shannon number. That's the number of terms we need to describe the function. And the powerful thing about this is that we have taken this continuous function described over all space and shown that we can accurately describe it without any approximation, 100% accurately describe the function with a finite number of terms. So we've taken the discrete function and turned the continuous function and turned it into a discrete vector of values. That's going to be a key capability for us in describing imaging systems. So what does this have to do with imaging? Well, here's a picture. It's a picture of some petroglyphs in Capitol Reef National Park that I took last summer with my cell phone. You see, it's a beautiful picture, but it's not the image. It's not the object. You know, the image has been blurred to some extent by the process of forming the image. Now, this image is defined over a finite area of support, so it satisfies the condition of having a finite size. But it also, through the process of imaging, has been blurred. And here I've blurred it a little more just to emphasize that this is a natural aspect of imaging. This blur effectively band limits the function. So it turns out that that the basic property of imaging systems is that they are band limited transformations of objects over a region of finite support. So this analysis we presented here today to describe these functions using discrete numbers and Fourier analysis is a fundamental piece that we'll be able to use to build forward models and understand computational imaging.